Hello and welcome to another episode of How to Understand X. Today we're going to be talking about mathematical beauty. We're not going to talk about any specific field of math, so this isn't going to be a calculus or trigonometry or geometry or algebra video. This is more just about math. Um, Math is just, well, I think I found this really nice quote by Bertrand Russell. Math is kind of like a quote unquote beauty cold and austere, like that of a sculpture, without appeal to any part of our weaker nature, without the gorgeous trappings of painting or music, yet sublimely pure and capable of a stern perfection such as only the greatest art can show. I think that's a very apt description of math. Um, Math is like the language of our universe. Um, we can observe things that are minuscule, impossibly small. We can observe things that are incredibly large beyond the scope of our sight. And we can see these things both across the universe and directly in front of us, and things that are so small that our eyes can't perceive. Yet, all of these follow math. They follow laws of physics, of thermodynamics, and these laws, the laws of physics and thermodynamics, and gravity and etc. I mean, gravity's physics, but you know what I mean. There's laws that this universe must follow, and all of these are defined by mathematics, which is insane. The fact that we as humans can observe math and see math and understand it and write about math and say, this is what our universe is founded on, and we are just like allowed to know that, to see that. That's just, I mean, it's insane. And the order of math, like the inherent beauty to math is that there are patterns to it. It's not just senseless. There is something, there's some type of structure to math that, and to the universe in general. There's this structure to math that seems just perfect. Math is in and of itself just, it's seemingly above, you know like humanity, like above us. And I mean, I'm getting a little bit, crazy right now, but math is just special. And, it's, again, the language of our universe. So we're going to talk about some beautiful things in math. This is going to be a relatively short video, I think. I'm only going to talk about some interesting proofs and ideas that I've seen before. I'm not going to go, any further than that. But let's talk first about Euler's identity. This is considered the most beautiful formula in math, and I would agree. Leonhard Euler, let me write out his name, was a mathematician, physicist, astronomer. He did a lot. Euler's identity is not. It's not even this. There's like a million Euler's identity, a million Euler's formulas, because almost everything is named after this guy. He's done everything that there is to do. But this is Euler's most famous identity. I'm not sure if he actually made this. I think it's just kind of named after him because, he was there. Not for this, but he was just there in general. And this is actually just an offshoot of Euler's formula, which I'm not sure if he actually made this or not. Um, Actually, no. I think that I think he did like do this. Um, but yeah, let's just kind of write out Euler's formula. That's e to the power of ix is equal to cosine x plus I sine x. Now this is beautiful in its own right. It establishes the relationship between exponential functions and trigonometric functions, which is odd, right? I mean, like, how do triangles and exponential growth have anything in common, right? But, you know, it's part of the beauty of math. But let's kind of do some stuff. So, let's just define. I'm not going to go into too much depth about this because I want to talk more about Euler's identity, but it's fun to kind of talk about the Euler's formula and to kind of say it. So, e to the power of ix is obviously a complex exponential function, right? I is an imaginary root. I is equal to the square root of -1, which does not exist technically. So we have to actually define e to the power of ix in some fashion that actually, is appropriate. So one of the ways to do that is just to do a nice mapping. So we can say that if z is some kind of a complex value that maps to e to the power of z, and then we can differentiate e to the power of z with respect to z and still get e to the power of z, where e to the power of 0 is equal to 1, then this fits all of our important ideas. This is e to the power of something, so that something is going to be a positive value, so 0 is still going to work. And it's a differentiable function, so we know that it's continuous, which is very important. So it still follows e because, e is a continuous function. And yeah, I mean, it's relatively simple. It just says if we can differentiate e to the power of z, that obviously makes it continuous, and it also ensures that z can be used as an input because we can differentiate with respect to z. So e to the power of z has to be a, if e to the power of z is complex, then this is a complex function that works. And, there is other ways to do this. I think you can use like the ratio test, because e to the power of z is the same as this sum, where your first is n equals 0, and then z to the power of n over n factorial. And the limit test, or not the limit test, the ratio test, it says that if you have one of these kinds of series, where I think it's actually n equals 1, but not for this one. When you have these kinds of series, you can just say that if L is equal to the limit as n approaches infinity of, the second term, a to the n plus 1, and the base case, or the first term, a to the power of n, then, well, actually, I think it starts with, this is the series, the first one. So a n is just like some case is happening, something is happening starting at n equals 1, where, something's going on somewhere. But yeah, if L, or this limit, is less than 1, then this series converges. If it does not, like if it's greater than 1, then it's divergent. And then if L is equal to 1, that's inconclusive. So we have to do, further testing. And yeah, so let's just kind of mess around with this. I'm not super familiar with ratio test. I mean, I've done it. I don't understand it at all. I'm not infallible. So I'm just going to simply rewrite this e to the power of z. I'm going to say that e to the power of z is the same as e to the power of z0 times e to the z minus z0. E is same base for both, so when you multiply these two, you're simply going to add these exponents, and those z0s cancel out, so we can get that n equals 1 and start at the correct, first one. And then we get e to the power of z is going to be equal to e, if we just, well, let me actually write it out, e to the z0, and then from n equals 0 to infinity of z minus z0 n don't know why I wrote it like that. Wish I didn't have to erase all of it whenever I make a mistake. Z minus z 0 to the power of n over n factorial, if we just, plug that into there. And so from here, we can just kind of say that if z0 is equal to 1, which it should, because e to the power of 0 is supposed to work, right? So e to the power of z is equal to e. E to the power of 1 is e. And then n equals 0, infinity. And then that's going to be z minus 1 to the power of n over n factorial. And now if we define some r where z minus 1 is less than r for a fixed r value that's greater than 0, then if z minus 1 is less than r, or the absolute value of z minus 1 is less than r, then you can say that from all of that, this is going to be less than or equal to e2 times this series, r to the n over n factorial. Again, we're saying that the absolute value of, let me try and not erase too much, e to the power of 1, which is e, and then z minus 1 right there. This absolute value, z minus 1, that absolute value, if this is less than r, that means that this limit, as n approaches infinity, of the base, it's not big L where n approaches infinity, it's lim, n approaches infinity of the second term over the first term, or z minus 1 to the power of n over n. If this is less than 1, that means this converges absolutely, which means that this is continuous. E to the power of z is continuous, which is what we want to say, because if e to the power of z is continuous, then z is a valid input for e to the power of z, which all of this was just to say that e to the power of z was a valid operation. So you don't need to know all of that. You can just use that differentiation thing, say that, oh, if I can differentiate e to the power of z with respect to z and still get e to the power of z, that means that, I'm doing something right, probably. And yeah, that's kind of how you can say that e to the power of ix should be a valid operation. Now let's talk about how to actually prove this. So let's write out. We're gonna do a proof. It's kind of difficult to fully explain. I didn't want to go into like polar coordinates or anything, even though I think that proof actually makes a little bit more sense. Teaching polar coordinates is a whole nother issue that I don't want to tackle right now. I simply want to talk about this kind of weird proof that I found online, even though I do somewhat understand it, but it's very odd. I do kind of get it though, so I'm gonna try and make it happen. But it's saying that f of theta is equal to e to the negative I theta times cosine theta plus I sine theta. The only reason that I'm doing this proof specifically is because it uses product rule, and we've been doing a little bit of differentiation. And this is what we are trying to do, is say that if the quotient of trigonometric and exponential function, so like if we write cosine theta plus I sine theta over e to the I theta, and we get a constant, like c, that means that there is some kind of a ratio that exists. And, well, the only value that we know works is e to the power of 0 equals 1. So c has to equal 1 at some point, right? And if e to the power of z, if this quotient is equal to 1, that means that e to the I theta is equal to cosine theta plus I sine theta. So if this is equal to that, when you divide it by itself, you're going to get 1, which is what we want. And we can do that by differentiating f theta. If we get f prime theta equals 0, that means that we know that f of theta has to be a constant. Derivative of a constant is 0. So if we know that f theta is a constant, and we know only one constant works as of now, that means that f of 0 is equal to 1, which means that f theta is equal to 1, and we'll talk about it, but I just kind of want to talk about what is kind of happening here, why we went to negative I theta. It's just so that we have a quotient. E to the negative I theta is the same as cosine theta over I sine theta times e to the I theta. And if this is equal to 1, if this is equal to 1, that means that this equals that. So that's good, obviously, because it proves what we want to prove. So let's do this. Derivative, it's relatively simple, it's just some relatively straightforward product rule. So it's this derivative times that plus this times that derivative. So f prime theta is going to be, what's the derivative of this? Well, it's going to be negative I, because this negative I theta, negative I is going to be a constant, so derivative of theta is going to be 1 if we're differentiating with respect to theta. So negative I times e to the negative I theta times cosine theta plus I sine theta. And then this is going to be plus this, just that, e to the negative I theta times this derivative. So that's going to be negative sine theta, derivative of cosine is negative sine, plus I cosine theta. Again, I is a constant, so we can bring that out, and derivative of sine is cosine. Now from here, let's just distribute these values. Negative I e to the negative I theta cosine theta plus, or minus, minus I times e to the negative I theta sine theta plus e to the negative I theta minus sine theta. Oh, whoops, silly me, I made a very slight mistake. When we have this I out here and this I out here, we get I squared, right? When we distribute those values together, and I squared is negative 1. So if we have a negative times a negative 1, that means we have a plus e to the negative I theta times sine theta plus e to the negative I theta, minus, forgot, we are distributing that minus from that right there. This needs to come out. So we have e minus I theta sine theta plus e to the negative I theta. Oh, I times e to the negative I theta. I was wondering why it didn't cancel out, because as right there, I times e to the negative I theta cosine theta. Now, negative and positive, this will cancel, and then positive and negative, these two will cancel. So all of this at the end should equal 0, which is what we want. If our derivative equals 0, that means that our antiderivative, or f theta, which is what we originally started with, is a constant. So if the derivative, which is f prime theta, is equal to 0, that means that f of theta, which is the antiderivative, is a constant, and the only constant that we know right now is 1. So that means that f theta is equal to 1, and yeah, that's pretty much it. Well, let me kind of write this correctly. We know that f of 0 is equal to 1, and since a constant never changes regardless of the input, that means that f of theta is equal to 1, right? We know that, well, let's just to make sure that everybody gets it, we have f of theta is a constant from all of this. We said that the derivative of f is 0, so if there is no change There's no instantaneous change, no average rate of change. If it's only 0, that means that it's a straight line, right? If we were thinking in terms of an xy plane. And if it's a straight line, it's going to be a constant. And we know exactly one value. E to the power of 0 is 1. So if f of 0 is equal to 1, that means that if this was an x, then f of x would equal 1. F of 0 is equal to 1, f of 1 is equal to 1, f of 2 is equal to 1, and on and on. So f of theta, because we're working with theta right now, is equal to 1, which means that, let me rewrite this. Cosine theta plus I sine theta over e to the I theta is equal to 1, which means that this, so e to the I theta, is equal to cosine theta plus I sine theta. I really like this proof. It's kind of confusing. I mean, you know, it's a weird one. It's definitely weird. But it's very smart. Like, you have to just say that if two things are equal, when you divide them by each other, you're going to get 1. And if we know that the quotient is 1, we know that the derivative should be 0, which we did get. And if we only know one value, which is f of 0 is equal to 1, then we know all of the values are equal to 1, which means that we know, like for sure, that the numerator equals the denominator, which is what we wanted to get in the first place. And now from here, we can just plug this in. So that was Euler's formula. Let me write it out one last time because it's, it's worthy of respect. It's a very nice formula. So we have e to the ix is equal to cosine theta, not cosine theta, we're doing x now, plus I sine x. This is a pretty useful, thing. It's used for defining complex logarithms. We know that e to the power of z is the base of some ln, right? If ln is equal to log base e, then e should be canceled out by e. So if we know that e to the ix is valid, then how do we do an ln of some complex thing? Well, we do need to do some manipulation. So let's write down what we're going to do. Let's say that a is equal to ln a. Again, this is pretty normal. We should be able to cancel out e and ln so that, this works. This is only so that we can define ln as the inverse operation of e. So if this is true, then, this is true. And also, e to the power of a times e to the power of b equals e to the a plus b. This isn't really used for actually proving anything. This is just defining the, I'm not going to say limits because, I have some self-awareness. But this just defines, what ln is and how e kind of works as a base. So from here, we can say that z is equal to the absolute value of z times e to the I phi. Phi is just, a letter. We use letters interchangeably. I mean, we just use theta instead of x for no particular reason. And then, because z maps to e to the power of z, this is a valid operation, And from here, we simply take, or not take, we have to do e to the ln of absolute value of z times e to the I phi. That was a weird phi. E to the I phi. And then from here, we simply add those exponents. Those are the same base, e, so e plus I phi. Again, I'm not doing my phi's correctly. And then this, we simply take ln of both sides. Ln of z is equal to the ln of the absolute value of z plus I phi. Okay, that was an okay phi. I mean, it wasn't great either. But, yeah, this is how you would take the natural logarithm of a complex number by taking the natural logarithm of an of a absolute value of a complex number and then adding that to I phi. So yeah, pretty cool. And there's obviously much more, applications. There's some like stuff about quaternions. That's like a type of number. It's weird. There's a bunch of sets, and so number sets. We were talking about this a little while ago in set theory. There's and natural numbers, R, real numbers, Q, rational. It just goes on and on. But quaternions is like some region of Euclidean space where there's a sphere of imaginary units. Quaternions is four-dimensional, and since quaternions includes imaginary units, we can actually, use Euler's formula for, some operations in there, which is good. And, e to the ix is a lot easier to differentiate than cosine theta plus cosine x plus I sine x. I mean, if I'm faced with some type of derivative, I'd much rather do a derivative of e than a derivative of any trig stuff, because derivative of e to the power of something is just the derivative of that something times e to that something. It's just e to the power of u. This derivative is equal to u prime times e to the u, which is pretty simple, so you don't have to do any craziness. And yeah, so now let's talk about Euler's identity. We're just gonna, plug in our values. We have e to the ix is equal to cosine x plus I sine x. So we had pi, e to the I pi is equal to cosine pi plus I sine pi. So let's draw a unit circle. Let's just say that this is pi, and this point's going to be negative 1, 0, which means that out here is negative 1, out here is 0, and from here, this is going to be 1. Opposite over, well, we're doing adjacent over hypotenuse, so this is going to be negative 1 plus I sine pi. Well, I'm not going to do that. We already know what this is. Sine is opposite over hypotenuse, and our opposite is going to be 0 over 1, so 0 is going to be, 0 over 1 is going to be 0. So e to the I pi is equal to negative 1 plus 0, and then we just add 1 to both sides, and then we get this nice e to the I pi plus 1 equals 0. This is considered one of the most beautiful formulas in math, and I'm inclined to agree. In case it's not impressive, let's just talk about both of everything that's not 1 and 0 for right now. E is the natural number. It's also called Euler's number, so, everything's named after Euler for some reason. But, it's not for some reasons, because Euler's, basically one of the greatest math guys to ever math. But, yeah, E is kind of everything. E is the limit as n approaches infinity of 1 plus 1 over n to the n. So, you would assume that this should be 0, right? 1 over n. We know that this approaches infinity because 1 over a very, very, very large number is going to be, okay. If, 1 over n is approaching infinity, then this is supposed to go to 0. Well, if n is approaching infinity, let me try to narrow there. If n is approaching infinity, then 1 over n approaches 0 because 1 over a very, very, very large number is going to be a very, very small number. So, yeah, we should get 0 for here, and then we should get infinity up here. And we know that 1 to the power of anything is 1, so 1 plus 0 to the power of, infinity should be 1 to the infinity, which should be 1, right? Not exactly. Infinity is an idea. It's not a number. So when you plug in, or quote unquote plug in infinity, you're just going to get 1 plus 0.000 dot 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 1 to the power of 1000 dot 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 0 at some point, most likely. So this and this, it doesn't get you an exact value. This is going to be very, very close to 1, but not exactly 1. And not exactly 1, after you do it to a very, very large power, you're not going to get anywhere close to 1. And that's why you get E, which is like 2.71828. Is it 128? No, it's 828. And, goes on and on. And then, whoops, pi is just like the circle number. It's the ratio between circumference and diameter. So C over D is equal to pi for any circle. And it's just it's kind of there. It's the circle. It's the circle number. And seemingly, well, E is also, the base of natural log, even though we did talk about that, but seemingly these have nothing in common. E has to do with, like, exponential growth, okay? E has something to do with, infinite limits and some crazy natural logarithms. It's very firmly planted away from trigonometry. And pi is geometry. It is very strictly circles and angles. And, like, the fact that we can come up with this formula, this connecting these two completely different numbers that seemingly have nothing to do with one another, even though we do know that they have a connection. We did do a derivative proving that they have some kind of a connection. For most intents and purposes, E and pi are kind of distinct. I mean, obviously they're distinct, but they don't have much to, like, intersect with one another outside of, like, calculus, where you're doing derivatives and integrals that use both E and pi. Like, operations don't typically involve E and pi together to have any kind of meaning. But the fact that we can just kind of have this relationship between these two seemingly completely different numbers. One is probably more calculus, algebra, and the other is definitely geometry, trigonometry. These two numbers, and these are both transcendental numbers. These are non-algebraic numbers. These aren't roots. These aren't rational. These aren't, numbers that we can go on for. E is a number that you can just continue calculating for the rest of your life, and you will just keep on adding more and more digits. Pi is the same way. You can keep on, finding more and more digits from that circumference of that diameter and be like, oh, here's another digit of pi. And you can just do that forever. These are both finite values. That's true. Because if you look at a number line, you can be like, oh, this is 2.71. This is 3.14. Pi and E should be somewhere around here. E and pi are not infinity. They're just decimals that do not terminate. And the fact that you can have these two decimals seemingly with nothing related to one another, these two completely different decimals, and I, square root of -1, irrational, not real, and you can have E, a transcendental, pi, a transcendental, I, an imaginary complex number, and have this composite operation, this exponential thing, this e to the I pi, and just get -1. Like a super simple answer. E to the I pi. Isn't that crazy? Like, these two numbers that have nothing to do with one another, e to the I pi, you just get -1. Like a super simple answer. And, what's also cool is 1 is there, 0 is there. These are, normal numbers, These are just things that we see. If you see 0 or 1 in an equation, you're like, oh, thank God, because, this is easy. And E, which is, complex to the point where we can't even calculate it fully. Pi, same way. I doesn't exist. E to the I pi, and we just get -1. Isn't that just, I mean, maybe I'm like, crazy. But most mathematicians, I think, are in agreement. This is crazy. This is just, it seems like it shouldn't be real. It's like, it seems too perfect because it's like a coincidence. It's kind of a coincidence, E, pi, they don't have too much in common. They're both transcendental. They both can't be calculated fully. They're both not roots. They're both real numbers, I guess. But like, in regards to what fields they're used in, E and pi, they don't have too much in common. And the fact that you just have this relationship between them, and you use a non-real number, but you get a real answer from this, that's just cool. That's just cool. And this is considered one of the best examples of mathematical beauty. You can have this very complex idea and express it in a very simple way. And yeah, I mean, you know, it's just it's pretty cool. So yeah, there's a lot of examples of Euler's identity. Uh, Euler's identity is used for, like, again, quaternions, like exponentiation. Is that a word? Exponentiation of those, like, 4D values in which, the imaginary unit is a sphere. Um, Quaternions use Euler's formula and, like, its derivatives, not derivatives as in derivatives, but like its children. Um, its children a lot. So, I mean, yeah, it's just cool. I mean, it's just kind of cool. And there's obviously more beautiful things, not more beautiful than Euler's identity, because again, Euler's identity is pretty much uh just, I mean, come on. It's just cool. It's just cool. We get E to the I pi. These things, these are complex numbers, These are not complex as in complex, but like, these are irrational numbers, so they don't have any terminating decimal. There is an imaginary number thrown into the mix. These are transcendental. These aren't roots, so it's not even, roots that we're working with. And we just get a super normal -1. That's just cool. That's just cool, And yeah, let's talk about some other examples of beauty in mathematics. Um, there's the partition of a set. I mean, set theory is considered, generally pretty beautiful because partitions are just ways to, separate the elements of sets. So let me write this out. Partition, grouping, or, separation of a set into non-empty subsets. I'm not going to go into too in depth into this, but partitions are considered beautiful for, a myriad of factors, but most usually because sets can be, infinitely large, as we've talked about in that set theory video. These can go on for all time, but we can actually just, partition them based on some type of like common characteristic between these subsets, and we can define equivalence relations, like, things that require. So equivalence requires bijections, injections, and surjections. I don't know why I put a comma there. Bijections, injections, and surjections. So these are, special. And for every partition of a set, we can just kind of do an equivalence. We can just have an equivalence relation. And yeah, I mean, it's pretty cool. We can, count them using like this series b n plus 1, so the second term is equal to n k equals 0, where you have n choose k times b k, so base case, and we just have, we got some stuff. This is gonna be, well, this is a recursion, so like, this is the base case, in like impacts the actual value, and you have to keep repeating this into there. But yeah, I mean, this also comes into like the Bell triangle, I think. It's somewhat similar to like what's it called? Pascal's triangle, in that it does, describe something in the in the form of a triangle. I'm not too familiar with Bell's triangle. I have seen it before. It's just a way to see the number of partitions. It's like 1, 1, 2, 2, 3, 5, and then 5, 7, 10, 15, I think. Yeah, you just have to, you copy it down, then you add, then you copy, then you add, then you copy, and then you add, and then you just, keep on doing that like pattern. And the fact that we can just do that and just see the number of partitions of a set, it's crazy that we can have this kind of a this kind of a rhythm inherent to set theory, supposedly one of the blandest things out there, and we can just have this like, this never-ending pattern that just works. It just tells you this is the number of partitions of a set, and it's pretty cool, It's also considered, another example of beauty. Proofs are considered beauty, not beauty, or beautiful when, like, I'm not gonna define a proof. We've been doing proofs a lot, but proofs are considered beautiful when they are simple and they use axioms. We have talked about axioms, and they're just things that are assumed to be true because we can't actually prove them. Like, these are super, super broad. Like, there is something that's infinite. You can add stuff like that. That's an axiom. Just like numbers exist. Very basic, like, framework for, actual proofs. If you can just describe something using, like, it's kind of like a proof is considered beautiful. So axioms are like the letters of math. They're just the very, very beginning. Because, speaking English and speaking any language, I don't know why English specifically, but any language is an assembly of letters and sounds, right? But the letters, they don't have any meaning by themselves. Like, what's the definition of D? What's the definition of like M? There's nothing. It's just a sound. But when you assemble a bunch of sounds and you like give them meaning through like just something that seems self-evident, that's considered beautiful. So if axioms are like the letters of the universe, proofs are like sentences. You just need to assemble your axioms in a way that makes sense and in a way that actually, communicates something interesting. And a proof is considered beautiful when it uses very, very little assumption. It's just axioms, it's very few corollaries, it's just idea. And this is the fundamental language of the universe. This is an idea. Oh, hey, just based on this, my idea works. And proofs are also considered beautiful when they're just like, snappy. They don't take too much time to prove. They're pretty easy. Like, I thought that that proof for the, what's it called? For Euler's formula was rather beautiful because it was pretty succinct, It was just, it was, you do this derivative, if you get 0, your original is a constant. The only constant that you have is 1. So this quotient is equal to 1, which means the numerator is equal to the denominator. That's a beautiful proof, in my opinion. And it's usually, proofs are also considered beautiful when it's like, you know, it seems crazy. Like, I mean, I didn't technically prove Euler's identity or anything, but it's considered beautiful because it's also weird, it's just kind of random. And yeah, I mean, that's what proofs are considered beautiful for. There's obviously, many different examples of beautiful proofs. For example, there's one of the most controversial proofs, I think, being the four-color theorem. It's just like, I forget the actual, fancy word. It's just no, like, region. If you color a map with 4 colors, no region, using using 4 colors when you're drawing a map, no region that connects to another has the same color as that other region. That's probably not, the most correct way of saying that. It's just like adjacent. That's the word that I want. Like, if two regions share like a border on a map, there's no way to draw a map using 4 colors where those regions have the same color. This is considered one rather beautiful proof because a human can't possibly do it. It's just, it was, I think, the first, or one of the first proofs to ever be, widely accepted, that was proven by or it might not be, widely accepted. I'm not sure how the mathematical community regards the 4-color theorem, but I know it was one of the first proofs that was, like, done with a computer. So that's why it's controversial, because, like, people are like, oh, it's not real, computers are dumb. It was back then. So I think now people probably are like, that makes sense. But it's just like the 4-color theorem. I think their methodology was that they just they created some kind of a plane, probably some type of a just one-dimensional plane of regions, probably like just a regular map. And they just said, given any like separation of this plane into any region, you can color any region 4 colors, any combination of 4 colors, and no 2 adjacent regions will have the same color. So yeah, I mean, you could draw the United States, you can draw every country in the world using only 4 colors, and they will never have colors that just, well, I mean, they could if you explicitly make it so, but you could draw it in such a way that no region connects to another one that has the same color. So yeah, I mean, that's pretty it's pretty weird to like kind of think about, right? Like that, using only 4 colors, any plane imaginable, you could just draw, and you can draw it without any regions that are adjacent to one another having the same color. I mean, there's obviously limitations. You can't have, like, forget what it's called, fractals, probably. I think it might be fractals, actually. It's just like they have a finite area but an infinite perimeter. That's not allowed. There's obviously like limits to that, but it's pretty cool. The Banach-Tarski paradox, I think that's also pretty. I talked about it a little bit in my set theory video. It's just you can. It's a paradox, so it's not super mathy, but it does talk about, why the axiom of choice is considered controversial. Banach-Tarski? I forget. But this paradox is just if you can split a sphere into a finite many, I wouldn't say finite many infinitely small pieces, but very, very small pieces. If you can break a sphere into a finite number of very small pieces, by the axiom of choice, you should also be able to create another ball of the same size that with those like same elements, which is insane, but also cool. It's a very interesting idea. Uh, like yeah, I mean, trying to trying to come up with something random. Uh, there's like the golden ratio. That's pretty beautiful. Like lots of things in nature. Like the ratio of like leaf growth and petals and stuff. I mean, there's obviously like a correct way of saying that, but lots of nature itself follows the golden ratio in terms of how like plants grow and how certain things develop in nature. So just the fact that we have a consistent ratio across different aspects of nature that can just describe how it grows in different ways, that's insane. That's just insane. We can just we can just keep on going, but I mean, like this isn't a very specific video. Um, there's the Permutahedron. That's pretty cool. Um, it's just if you have a shape that is of like n dimensions, well, not n dimensions, it's n minus 1 dimensions. So you have order n, or like the number of nodes, like nodes isn't probably the correct word, but you can just like describe like shapes or polygons, not polygons, but like so I'm floundering out here, but if you this is a cube, right? I know, pretty crazy. I would call this nodes. So a permutahedron has n number of nodes and then n minus 1 dimensions, which is pretty cool. Like, this is, specifically a permutahedron. And it just, the fact that you can just do that for any order of n is pretty ridiculous. It's not called a node, it's called a, like, vertex. Yeah, it's just the permutations of the first n natural numbers. So, like, first 2, first 3, depending on how many, depending on how high your order of n is, your, like, vertex coordinates are just going to be, defined differently. And the fact that you can just draw a permutahedron of different orders and have, like, crazy looking shapes with several different dimensions of measure, that's pretty cool. Um, you know, uh, there's like, I feel like, remember reading something about the mathematics of folding, uh, how like exponential growth can be modeled by like pieces of paper being folded over one another, and how you can just kind of like there's lots of things. There's honestly just lots of things in math, and you might think that math is just a dry, boring subject where you don't learn anything that's useful. And for some people that might be true. Maybe you go into like a field that doesn't use mathematics at all. But I think just in general, um, math is math is pretty cool. um, just to sum up everything that I've been talking about, math is just it's beautiful. It's genuinely beautiful because it's the description of our universe, our observable universe through our lens. And using axioms, using the letters of the universe, things that we have to assume, just things that we things that are so incredibly basic. I just stuttered way too much. Things that are so incredibly basic that even just the idea that we can split things and we can choose how things are partitioned, that was considered controversial. The idea that axioms, some of the most basic building blocks the basic building blocks of formulas, which are the basic building blocks of math, using just axioms, using the bare minimum, we can create crazy stuff and we can define laws that just apply to our entire universe. And there's just so much math out there. I mean, yeah, math is beautiful. It truly is just, as Bertrand Russell said, it's just a beauty cold and austere. You know, it's it's perfection. It's beyond us. You know, I don't think we deserve math. Might be a good way to say it. Like, I don't know. I don't want to nerd out too long because I feel like I'm just ranting at this point. But math is just, it's beautiful. It's just genuinely beautiful. The fact that we can, as humans, just come up with some very, very basic ideas, things that just seem obvious, and from that, develop calculus, develop these insanely detailed fields of mathematics where things are still consistently growing, where things are consistently being discovered. I mean, yeah, that's crazy. And I hope it kind of like, I don't want to, stand on a soapbox and be like, you should do math. But I mean, if you are already doing math, I think that's just kind of a sign that anybody can do math. And anybody can achieve something in this field because math will never end. There will always be something to discover, something to create, another proof to find, another idea to define. There's just so much math out there that needs to be mathed, and we need more mathematicians to math. And yeah, that was a somewhat, not somewhat, very disorganized rant about the beauty of mathematics. We did talk about some cool stuff. I liked that proof of Euler's formula. We did talk about Euler's identity, a little bit about the logarithm, like complex logarithms. We did very briefly touch on some set theory and, some stuff. But yeah, I mean, just in general, math is very beautiful. And there's so much math out there to be mathed. And I encourage you to go out and math. This is a shorter video, so I'm not actually going to recommend an album, but I am going to recommend a song. Hold on. Let me get my pen. Math. Math, okay. What am I talking about? I have math in the brain. It is also rather late, but let's talk about something that I listened to very earlier today. I mean, this song just came out like 3 hours ago. It's technically about 1 a.m. right now, so um, it did come out like, I know, a little while ago, but it is called Traffic by Reggie. Well, his actual name is Reginald Helms Jr., but Reggie is his stage name. Listen to this man's music, all of it. It'll take you 10 to 15 minutes, and you will be emotionally punched in the face. That's how I felt. I was simultaneously, not simultaneously. I went from happy after listening to Avalanche and seeing him grow, and then depressed, like just miserable, from I don't want to feel anymore. Southside Fade. I don't know how I feel. I feel like nostalgic for that one. It does remind me quite a bit of, certain parts of my life. But yeah. I mean, we've we've obviously lived very different lives, but I've seen similar communities to the one that Reggie has, or that like similar um, a similar world. I've seen similar stuff, but you know, it's just, and Southside Fade's obviously fantastic. Avalanche is great. Traffic. I mean, I've listened to it twice. It's already, stuck in my head. It's very, very well done. I mean, everything that he's done is well done. It's just like, I don't know. He has a very good discography because he doesn't have a very large one, but honestly, I think he definitely does have quite a bit of potential. Oh, he did like a collab track with Kenny Beats. What was that called? It was oh, it was really good. I do remember it. Oh, Ain't Gonna Stop Me. That's a good one. That's a good one. That's also inspirational. So it's like depressing, inspirational, nostalgic, happy. Like it's just it's very it's very unique. It's this kind of odd neo soul hip hop thing, and Reggie has this very specific croon that is instantly recognizable. I think if you listen to maybe two of his songs, oh, he does have a falsetto. It's pretty hard to tell that it's actually him. It took me a while to know, or to even like, guess that the voice on "I Don't Want to Feel No More" was Reggie. That was surprising for me, but he does have a very distinct falsetto. But in general, he just has this like croon that's very Reggie, um, and that's impressive for someone of only like 6 tracks. I mean, they're not perfect. They're like 2 minutes. He doesn't flesh out his ideas as much as we would like, but yeah, just listen to this man's discography. It's essentially perfect because he didn't have as many opportunities to mess up as other artists, but you know, with a more consistent schedule of how he like releases music, I think he could definitely be one of uh, the best artists in his very specific like niche. And yeah, Traffic's a very good track. Listen to it. I'm not sure where it would rank in my current ranking of his discography. I think Avalanche, then Ain't Gonna Stop Me, then Ain't Gonna Stop Me and I Don't Want to Feel No More just kind of bounce around for me. And then Southside Fade, and then actually no, Southside Fade might go a little bit above. I mean, obviously you can tell I'm having a bit of trouble because all the songs are essentially perfect for what they are trying to be. But yeah, listen to Traffic. If you like it, please comment down below. And if you like this video, also please comment down below. If you did not like this video, constructive criticism is always encouraged. And if you're not in the mood for a comment or constructive criticism, then you can. Oh man, what's an exercise? I keep running out of exercises. I don't do enough. Do some hammer bicep curls. Like the ones where you just like have them 90 degrees. Use a lighter weight for these ones. They mess up your forearms. Like, I mean, not mess up as in like deform them or anything, but they do. They hurt. Yeah. Just do some hammer curl ups, and also, I know I'm talking a lot about the order of the universe. Please do not talk about God in the comments. Don't mention that dude. I don't know what they're like doing up there, but they don't need to be part of this conversation. You know, God's not math. Uh, Obviously, there are some patterns that we have observed in the universe, but please don't talk about God. Nobody wants to hear that. Not in like a atheist way or like a I don't care about your religion way, but more in like a math is what we're talking about right now. So let's keep it strictly about math. But yeah, listen to Traffic by Reggie. Go on and math in this universe. And bye.